Let's look at gas stoichiometry, and we have our TEECs listed here. We need to be able to perform stoichiometric calculations, including determination of mass and gas volume relationships. We're going to do a couple of fairly easy problems here using RICA tables. Go back to Avogadro's hypothesis, one of the foundational theories of chemistry. Avogadro stated that equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. Therefore, if we know how many moles of gases react, that is, if we have the balanced chemical equation, and the temperature and pressure are the same before and after the reaction, the volume ratio of the gases would be the same as the mole ratio of the chemicals. For example, we know that 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of steam, that is, water vapor. Now, if the hydrogen, oxygen, and steam are measured at the same temperature and pressure, for instance 500 Kelvin, maybe 2 atmospheres, the same before and after the reaction, then we could also say that 2 liters of hydrogen would react with 1 liter of oxygen to form 2 liters of steam. Now, we find that pentane, C5H12, will react with oxygen gas. It'll react completely and form carbon dioxide and water vapor. So turn off this and write the balanced chemical equation, and then come back and check it. Here is the equation. You see that the ratio of moles is 1 to 8 to 5 to 6 on the product side. Now, if we have that balanced chemical equation, and we are at 500 Kelvin and 1 atmosphere, and we can use any place where everything is a gas, any temperature and pressure, so that doesn't change. We mix 1.5 liters of pentane with 15 liters of oxygen. We can ask the question, how many liters of pentane, oxygen, carbon dioxide, and water vapor, if they're measured at the same temperature and pressure, would remain after the chemical reaction is over? This is an ideal problem for a RICA table because we want multiple answers here. And so here's your RICA table. The reaction is always written with the coefficients on the chemicals. And so we have that on the top line, the R line. And the problem is given down at the bottom so you can follow it. Now, since temperature and pressure don't change, we know that the volume ratios that we see here are going to be the same as the mole ratios. That way we can use liters, not moles, in the RICA table. So we have 1.5 liters of the pentane and 15 liters of oxygen. To begin with, we have no carbon dioxide and no steam. The oxygen needed is 8 times the volume of the pentane. So the volume of the oxygen is 8 times 1.5 liters, or 12 liters of oxygen. So we're going to burn all the pentane, all 1.5 liters of pentane, but only 12 liters of the oxygen. That means that the oxygen is in excess and the pentane is limiting. Liters of hydrogen oxide, that is water, steam, and carbon dioxide formed. We see 5 liters of carbon dioxide are formed for every liter of pentane, and 6 liters of steam are formed for every liter of the pentane. And so we do that multiplication and we see that 7.5 liters of carbon dioxide are expected, 9 liters of steam are expected. We've used all of the oxygen and all of the pentane. So we can add up each column to see what is going to remain after the reaction. Now there's no pentane left because we used it all. There'll be 3 excess liters of oxygen, and of the products we have 7.5 liters of carbon dioxide and 6 liters of steam. If, of course, the temperature and pressure changed, we could take these numbers of product and we could put them through the Pave-Nert equation to see what they would be at the new temperature and pressure. There's a second type of problem that we would like to look at, and that is we're given grams of reactant and or moles of reactant, and we need to find the volume of the gaseous product. So we'll get a little bit more difficult question here. We know that magnesium reacts with hydrochloric acid to form a solution of magnesium chloride salt and a gas. So turn off the, or stop the projection and write the balanced chemical equation for this magnesium hydrochloric acid reaction. Then turn it back on. There is your balanced chemical equation. We've used a little script L for the Cl so that you wouldn't think that that was a 1. And you can see there's a 2-to-1 ratio of moles of hydrochloric acid to magnesium. Here's the question. If 4.8 grams of magnesium are mixed with 500 millimoles of hydrochloric acid, how many millimoles of the two products would be formed? What will be the excess reactant, and how much will be left over? And how many liters of the gas at STP will be produced? This might look very complicated, but really does yield to a RICA table. And here we have it with the coefficients on the reaction line. And the question itself is down at the bottom. Now, the initial magnesium is given in grams, and of course we can change that to 4,800 milligrams. We then multiply by 1 millimole per 24 milligrams of magnesium, and we see that we have 200 millimoles of magnesium. Now, we have 500 millimoles of hydrochloric acid, and of course 0 product. So let's see how much hydrochloric acid we will need for all 200 millimoles of magnesium. Well, if you look at the balanced equation, you see you need twice as many moles or millimoles of hydrochloric acid as of magnesium, and 2 times 200 is 400. So we need 400 millimoles of hydrochloric acid to react with all of the magnesium. So all of the magnesium reacts, but the hydrochloric acid is in excess, as it usually is when we have equations like this. If we look at the balanced equation, we see that the coefficient on the magnesium, magnesium chloride, and hydrogen gas are all the same. Therefore, we'll produce, or expect to produce, the same number of millimoles of magnesium chloride as we had millimoles of magnesium. So we have a 200 additional on the salt and on the gas. We then add all of these numbers up, and we see we have used all of the magnesium. We have 100 millimoles of hydrochloric acid left over. That's in excess. We have 200 millimoles of magnesium chloride salt in solution, and we've produced 200 millimoles of hydrogen gas. We now have the final part of the problem: how many liters of the gas at STP will be produced? Well, we have to remember that these millimoles are millimoles, not moles. But it's at STP, so there will be 22.4 milliliters of gas produced for every millimole of the hydrogen. So the ratio of millimoles to, milliliters of gas to millimoles is the same as it is liters to moles. And if we look at this calculation, then we see that the milliliters of hydrogen would be 200 millimoles times 22.4 milliliters per millimole, or 4,480 milliliters. Now that's really only got 2 or 3 sig digs here. In fact, 2 significant digits based on the original amount of magnesium. And therefore we would change this to liters and have 2 significant digits. 4,480 milliliters will round up to 4.5 liters. And this is the answer to this second type of problem.